All right, the final thing to teach you. Titration. This is the best lab. There's no way around it. This would have been the best lab to do. Colors and chemicals and all sorts of stuff. But we don't do that because of this. So let's just talk about it. What a titration is, and there's a video of me doing a titration. It's basically you're trying to determine what the concentration of either the acid or the base is. And the way you do that is you must know what the concentration of one of them is, and also know how much you use of each one. So if I use a certain amount of acid and I know its concentration and I know how much unknown base I use, I can figure out what the molarity or concentration of that base was based on all that. And that's what a titration does. And it uses the phenomenon that protons plus hydroxide ions, H plus plus OH minus, make water. And at some point, if you're titrating an acid with a base, you're going to make it into water. And when it's water, you know all of the acid and all of the base are equal. Okay, so we call that the equivalence point. And the equation we use for this is just the molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base, which basically means that the moles of the acid will equal the moles of the base, and hence you'll have water. So this is like a Space Invaders game. Let me show you a Space Invaders game, because why would you know what a Space Invaders game is? This is a Space Invaders game. This is what we used to play when I was a kid. So if all of these things up here, the aliens, are acid, and I'm shooting base at it, I can turn each acid into water. It doesn't mean that because I've added some base that it's all water. It's just some of the acid is now gone and become water. See how that works? So yeah. All right. Let's get out of here. Right die. All right. So that's what's happening here. We have a whole bunch of acid, and I'm shooting base at it, and that's exactly what you're going to do when you do. So all of these things are, let's say, acids, and I'm shooting base at these acids. And when one base hits an acid, I make water. So if an OH were to hit any one of these, it'll turn into water. The good news is, right, that turns into water. The bad news is I still have all these other acids out here. So there's still plenty of acid left after that happens. So the solution will still be acidic. So I have to keep hitting it with base until all of these H pluses are gone. So just assume all those aliens have an H plus on them. I just can't draw that much. And I made this picture myself, actually. But I ran out of patience. All right, so that's what an acid-base titration does. So basically, remember from anything you've ever taken in math that the word of means times, right? So you're going to multiply this times that, and this times unknown. So that'll be your x. So 30 mils. So in this case, that's the base, right? This is the base, and this is the base because it's KOH. So 30 times 0.5 is going to equal 10 times x. And the x will be the molarity. The x will be the molarity of the acid. So there you go. So this turns out to be 15 equals 10 MA, and then MA equals 1.5 molar. And there you figured it out. So that's how you do titration. Look at the lab of me playing with the titration. I really wish we could have done it. It really is the lab everyone enjoys. But unfortunately, it did not happen. All right. Here's a graph of what happens. So as you add base, right, as you're shooting base at the aliens, it stays an acid until the point where all of that acid is gone. So there's a point where all of these H pluses are gone, and that is called the equivalence point. So here is where you have water, right? Everything turned into water, and the next drop of base you add will now, because there's no acid to take it away, turn it basic. Thank you. Turn it basic and more basic, and soon you'll just fill up the beaker with more and more base because there's no more acid to take it away. All right. There you go. So the other thing we should learn about is, remember we talked about Bronsted at Lowry. Acids are proton donors and bases are proton acceptors. Um, so this is basically, because that happens, I should stop saying basically when I'm teaching this. Um, an acid is anything that can give up an H plus. Okay, so if you give up an H plus, you're an acid, and if you pick up that H plus, which is what happens here with ammonia, then you're a base. So because of that, after the reaction, if you have an acid, say in this case water, reacting with a base, which in this case is ammonia, after that happens, now the base becomes an acid because it now has an H to give back to something else. All right, so think about this as like a game of tag, or if we're going to play heads up, 7-up. Here's the H plus on the water. When that H plus is given to ammonia, now ammonia has it, and it's the acid. This is now the acid, but we call it a conjugate acid because it happened as a result of this. And now this is a conjugate base because it can now accept a proton. It's missing one. So we call that a conjugate base. Okay, whereas originally this was the base and this was the acid. So what you're going to be doing in your review this week is trying to identify which is an acid, which is a base. So here, the thing that lost the H is the acid. The thing that picked up the H is the base. Okay, this picked up the H to become that. So this was a base. Now it's an acid. This was an acid. Now it's a base because it lost the H. After you've lost an H, you become the base. After you gain the H, you become the acid. And we're going to play some heads up, 7-up to hopefully explain that. Okay. So that's Bronsted Lowry. Let's talk a little bit about buffers. So when you watch the video or whatever, as you saw here, when you have a strong acid with a strong base, there is no resistance to changing from very extreme ends of pHs, right? So here you have your high pH, and down here you have your low pH, and there really isn't much in between. It's a very little bit amount of base added when you're in that little between. So not unlike what we're doing right now, buffers, what they do is flatten the curve, is they make that curve sort of less severe, so the pH goes higher up. It's not as low, and it doesn't go as high. Okay, so it starts around 4 and it goes up to maybe 10, and that kind of controls things. More things can live between 4 and 10 than at 14 and 1. Okay, and the way we do that, like your blood would be in really bad shape if it did not have, if its pH could get all the way down to 1. If you had pH 1 blood just because you had a spicy meal, which had some acid in it, that would not be good for the rest of your organs. So what we do in our blood and or anything, what we do is we call it a buffer. And what a buffer does is it converts a strong acid into a weak acid. Okay, so strong acid, right? The H plus is off the leash. If we put a bunch of weak acid into a solution, what would happen then? Right, you have these anions. So let's say these anions here that you see are like, let's call them like acetate, C2H3O2 minus 1. So that's a weak acid. So that's what this blue thing is. And if you put some acid in there, what's going to happen next? Well, if you throw some acid in, that little, this anion's going to attract it, and then we're going to have no charge. And it's going to become one of these things, which means that H plus is tied up, which means you took a strong acid and this weak base from acetic acid, picked up that H and doesn't let go of it like the strong acid did. And so now the pH isn't going to be as high. You turned a strong acid into a weak acid. Likewise, what would happen if you put some strong base in there like OH minus? All right, so if you put some strong base like OH minus, what happens next based on the definition of base? It's going to pull that H plus off and turn into water. And when it turns into water, what's going to be left is a very weak base, which does not have as strong a pH issue as the strong base did. So you're turning pH 14 into like pH 10, and you're turning pH 2 into pH 4 by having the presence of this mixture, basically, of a weak acid and weak base. So that's what buffers do. Buffers will flatten that curve. So instead of having a curve like this, you'll have a weak acid, so it won't be as much there, and a weak base, so it won't be as bad there. All right. The last thing you should know for acids and bases is what a Lewis acid is. So we've been talking about how Bronsted Lowry said a proton has to sit on top of a base for that to be considered a base. And what Lewis acids came up with is like, well, why does it have to be a proton? What if any sort of freeloader, like this guy, right? Any freeloader that hangs out on a lone pair, why can't we just call that an acid and the lone pair guy who's holding this thing up a base? And so that's not untrue. So boron can only make 3 bonds, so it has basically an empty area for electrons. Nitrogen has a lone pair, so what's to stop boron from saying, hey, you know what, I'd love an octet, let me just hang out here with this nitrogen and pretend that's my electrons too. And so boron here would be called a Lewis acid, because it's basically mooching off of the electrons. Thank you for that again, right? Mooching off of these electrons from ammonia. And we would call this a Lewis base. So basically what Lewis said was, why does it have to be a proton that sits on those electrons, right? That's what Bronsted Lowry said. Protons have to sit up here and do this. And what Lewis said is, why does it have to be a proton that sits there and occupies those electrons? What if it's just anything? So anything that sort of sits and occupies electrons is called a Lewis acid, which should be drawn in red, and anything that gives those electrons away is a Lewis base. And if you go on to AP Bio, you're going to learn about amino acids, right? Amino acids are sort of like this. They have that acid end, okay, and they have their amino or their basic end. And so that's fun because sometimes the base wants to give the H's, wants to take the H from the acid, right? Because this is an acid, so it wants to give its H over here to the base. So often they'll exist like that, where the carbonyl carboxyl group is negative and the amino group is positive. So it's still overall neutral, but because there's a base on there and an acid. Anyway, and then there's some R group on every amino acid. There you go. That's everything you need to know about acids and bases. I hope that was helpful.